Okay, I just briefly wanted to show that the coordinates of x was b transpose x. Um, so just as a reminder, our matrix B is the set of vectors v1 through vk. Right, so b transpose would be v1 transpose vk transpose. Now this was n by k, so this is k by n, right? And so what happens when you take b transpose times x? You get the, oops, I don't want to make that equal to each other. I want to make that equal to each other. My eraser works. So therefore b transpose x is going to be, I'm just going to multiply this vector here by x, so that's v1 transpose times x, vk transpose times x. And from what we saw over here, we said that c sub j is x dot vj. And what you see here is that this is x dot v1, and this is x dot vk. Good. And so that is a vector of our coordinates. So that is the set of coordinates of x with respect to b. Good. All right. Now I should say, by the way, that we're not going to be doing this by hand. We're going to be using the computer to do this. My eraser doesn't work good anymore. Okay. I don't know why my eraser stopped working, but I guess I don't need an eraser. Okay. Where else are... Okay, I'm going to pause for a sec. Yeah, I've located myself again. So what's interesting to notice here is that this equation now translates to something special. So x is equal to b times b transpose times x. So doesn't that mean that bb transpose is the identity? Well, that's an interesting question, because not always is that true. There's going to be some examples in the notes about that, but as it turns out, this matrix b times b transpose, by the way, what is the size of this matrix? B is n by k, so this is n by k times k by n, so that's going to be an n by n matrix, right? So this matrix takes in a vector from Rn and puts out a vector in Rn. This is a projection matrix, projects vectors to the k-dimensional subspace defined by the orthonormal vectors in B, right? By that I mean those are the basis vectors, the columns of B. Okay, and so what happens is, let's do a little computation. Let's let B be equal to V1, gosh darn it, V1 through Vk. That's going to be n by k, and let's suppose that B has orthonormal vectors. Right? Let's see what B transpose times B is. Okay, so I'm thinking, by the way, that B, I'm thinking about the size of B for just before we start. Can B be, I'll write this off to the side. I'm used to talking about this in class. It's hard to, I'm usually not writing it down. Can B be a tall matrix? Can B be a wide matrix? Let's see. So can B be a tall matrix and have orthonormal columns like this? Yes, it can. And in fact, it usually is. Yes. Good. Can B be a wide matrix? Absolutely not. Did you say no? Why isn't my color showing up? No. No, no. I wanted a red. No. Why can't it be wide? Because then the columns would not be linearly independent, right? If a wide matrix always has columns that are linearly dependent. Okay, so therefore this B is always going to be a tall matrix or square. And so what is B transpose B? Is it the small k by k? It's k by k. I just gave it away. This is k by k. And so think of it as the small square matrix. Right? And so, in fact, if we take a look at what that is, that's going to be V1 transpose down to VK transpose times V1 VK. That's equal to V1 transpose V1, V1 transpose V2. Oop, I'm running out of space. Oh no, my eraser doesn't work. Oh, now it did. Okay, I don't know what's going on there. Having a tough time here. Okay, this is my matrix. And the next row will be V2 transpose times V1, right? V2 transpose times V2. Dot, 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 dot. Okay. Dot, dot, dot. And then the last column, or last row here would be VK transpose times V1 dot 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 VK transpose VK. Do you see along the diagonal what's going to happen? Along the diagonal we get ones because we're orthonormal. These are the magnitude of the vectors. And off the diagonal we get all zeros. And so this is the identity matrix, k by k. Good. Okay. Is BB transpose the identity matrix? That's the big question. And that was V1 to VK times V1 transpose to VK transpose. If I just compute out what this is going to look like, gosh, I don't know what happened to my eraser. Oh gosh, it's probably going to vanish here in a few minutes. Okay, this is going to be equal sign. I don't know what's going. Oh, there it goes. Okay, I just have to be gentle with it, I guess. That's going to be V1 transpose plus V2 transpose plus VK transpose. And careful, what are each of these vectors? Or what is each of these expressions? We can play the scalar vector or matrix game. Are these things scalars, vectors, or matrices? They are matrices. Each one is an n by n matrix. N by n matrix, n by n matrix, n by n matrix. Yes, and so this is not going to be the identity typically if B is not square. If B is not square. Okay, if B is square, we can show that we get the identity matrix either way. Okay, good. And so what is BB transpose? Well, from our work over here, what we showed is that BB transpose is a projection matrix. So if B is a matrix with orthonormal columns, then BB transpose is the identity, but BB, oh wait a minute, did I just say that? It's not the identity. I missed the, there we go, there's the other one. Let me re-summarize. Trying to erase things. I'm gonna have to fix my eraser before I do this again. So summary. If B has orthonormal columns, then B transpose B is the identity, but B B transpose is not the identity. In fact, B transpose projects vectors to the subspace. Do you remember what that is? Spanned by the columns of B. Okay, we made it. So where are we in the notes here? We finished page 41, and so go ahead and work through the exercises at the bottom of page 41. So exercises are at the bottom of page 41, and we'll take maybe one more video on the 4 fundamental subspaces. I think we can fit that in. I don't want to get too carried away here on a Friday. We'll stop there. Yes, I think we'll stop here for now, and we'll do the 4 fundamental subspaces on Monday. Something to look forward to. Okay, see you then.